You've probably heard the saying, numbers don't lie, right? Well, what if they don't tell the whole truth? Today, we're going to dig into a really cool statistical puzzle that proves why just looking at your data is as critical as crunching the numbers.
Okay, so let's start with a little test. Are these four data sets the same? I mean, just look at them. You'd think, no way, they're obviously different. But what if I told you that on paper, statistically speaking, they are practically identical? Kind of weird, right?
And I'm not kidding. If you just run the numbers, the basic summary stats, the evidence is, well, overwhelming. For every single one of these data sets, the average of the X values is 9. The average of the Y values, 7.5. Even the variance is pretty much the same. And the correlation, which is just a fancy way of saying how strong the relationship is between X and Y, is a solid 0.816 for all four. So, case closed, right? They've got to be the same.
Yeah, not so fast. This is where things get really interesting. What you're looking at is the core of something called Anscombe's quartet. It was put together back in 1973 by a statistician named Francis Anscombe. See, he was getting tired of people thinking that, quote, numerical calculations are exact, but graphs are luff. He set out to prove, once and for all, just how misleading those exact numbers can be when you don't have a picture to go with them.
All right, let's actually look at the first data set plotted out. And this one, well, this one is exactly what you'd expect to see. It's a nice, simple, clear, linear relationship. All the points are kind of clustered around a straight line. The stats we saw earlier, they describe this picture perfectly. So far, so good. But now, look at dataset number 2. Remember, it has the exact same statistics, but it tells a totally different story, doesn't it? There's definitely a strong relationship here, but it's not a line at all. It's a perfect curve. So, trying to describe this with a simple linear correlation, it's just wrong. It's completely misleading. Okay, on to dataset number 3. And wow, look at that. We have an almost perfect straight line, except for that one lonely point way up at the top. That one little troublemaker is pulling the entire trend line off kilter. It's single-handedly responsible for dragging the correlation down from a perfect 1 to that same 0.816 we saw before. And this last one really drives the point home about the power of a single point. In our fourth dataset, almost all the data is just stacked up vertically. There's no relationship there at all. But then you've got this one extreme outlier, way off to the side. And that one point all by itself creates a strong statistical correlation that is completely and totally artificial. So that common villain we saw in a couple of those plots, it has a name, the outlier. You can think of it as the master of distortion. It's that one data point that can bend, break, and sometimes just completely make up statistical results that aren't really there. So what is an outlier officially? It's really simple. It's just a data point that's way far away from all the others. It's that one unusual value that just doesn't seem to fit in, and it can cause huge problems for our analysis by twisting the real results. Let's put this into a real-world context. Imagine we're measuring the height of 15 guys. Now, with just one outlier in the mix, the average height comes out to 2.4 meters. That's almost 7'11". Crazy, right? But if you take that one person out, the average drops to a much more normal 1.8 meters or about 5'11". That is a massive difference, and it's all because of one data point.
And check this out. Look at the standard deviation. That's just a measure of how spread out the data is. With the outlier, the spread is a whopping 2.3 meters. Take him out, it drops to just 0.14 meters. That one single point changed the statistical spread by more than 7 feet. It completely changes our understanding of how similar or different the people in this group are.
So, the big question is, how do we protect ourselves from these kinds of statistical illusions? Well, it's all about using the right tool, and in this story, the hero is the scatter plot. Think of it as your own personal data detective's magnifying glass, ready to find the truth that's hiding behind the numbers.
Of course, you gotta know when to use it. A line chart, for example, is perfect for tracking changes over time, like how the temperature goes up and down during the day. But a scatter plot, its special job is to show you the relationship between two different things, like height and weight, or, in our case, those X and Y values.
And the good news is, they're actually pretty easy to read once you know what to look for. It's just 3 quick steps. First, always check the axes. What are we actually comparing here? Second, just kind of squint and see if you can spot any natural groups or clusters. And finally, look at the overall shape. Do the dots make a line?
A curve? Or is it just a big random cloud of points that tells you there's probably no relationship at all?
So now that we have our magnifying glass, we can officially become data detectives. Our job is to actively hunt for that odd one out. Just spotting these clues is the critical first step to doing a much more honest and accurate analysis. So, what does a clue look like? Well, the most obvious one is an isolated point just floating way out in space, far from the main cluster. But you can also look for points that just don't seem to fit the pattern that everything else is following. And hey, other charts can give you hints too. An isolated bar in a histogram, or one of those little asterisks you sometimes see on a box plot, those are both screaming, hey, you've got an outlier over here.
Okay, so to make sure we don't fall into these traps ourselves, it helps to have a simple field guide. Just a few basic do's and don'ts to keep our analysis on the straight and narrow.
Here's the cheat sheet. Rule number 1, do. Always graph your data first, before you do anything else, which means don't just blindly trust those summary stats. Next, do investigate your outliers. Figure out the story behind them. Was it just a typo or something genuinely interesting? Which leads to don't just delete them without a really good reason. And a little pro tip for you, if you've got a ton of data points, do use some transparency so you can see where they overlap. And don't make your charts so crowded that nobody can read them.
And let's wrap up with probably the most important phrase in all of statistics. Correlation does not imply causation. You've got to drill this one into your head. Just because two things seem related on a chart doesn't mean one is causing the other. The classic example is ice cream sales and the number of drownings. They're highly correlated. But obviously, ice cream isn't causing people to drown. The hidden variable is hot weather. When it's hot, people buy more ice cream and more people go swimming.
So at the end of the day, summary statistics will give you the headline. But the real story, that's almost always hidden in the visual details. So the next time you're staring at a spreadsheet packed with numbers, remember Anscombe's quartet. And just ask yourself one simple question. What story is really hiding in my data? Because the only way you're ever going to find out is to actually look.